Yeah, hello, I'm Antanas Kalkauskas from Nanyang Technological University, Singapore, and I'm going to talk about updating WasmCert-Isabelle to WebAssembly 2.0. So, the language standard of WebAssembly supplies pen and paper formal model of language semantics, and this formal model can be mechanized, that is encoded in interactive theorem provers, and those mechanizations can then be used to verify properties about the languages, such as type soundness, or to derive formally verified artifacts, such as type checkers and interpreters. And this has been demonstrated by the WasmCert project. So WasmCert project consists of two sub-projects: WasmCert-Isabelle, which is Wasm mechanization in Isabelle HOL, and WasmCert-Coq, which is a mechanization in Rocq. So WasmCert-Isabelle was the first Wasm 2.0 mechanization, but since then it has been overtaken by WasmCert-Coq, which was the first to mechanize Wasm 2.0. Still, WasmCert-Isabelle has been previously extended to cover some of the extensions of Wasm 2.0, such as SIMD and multiple value proposals. And now it has just been fully updated to Wasm 2.0, which is the topic of this talk. And the main tasks to update to Wasm 2.0 was to extend WasmCert-Isabelle to cover bulk memory operations and reference types proposals. So the update touched most parts of WasmCert-Isabelle, including definitions, which include typing rules, reduction rules, and other language structure, the type soundness proof, verify type checker, interpreter, module checker, and instantiation procedure. The added bulk memory proposal, it introduced new instructions for bulk memory operations, such as memory copy and memory fill, which are similar to memcopy and memset functions from the C standard library. It changed the module structure, in particular element and data segments, which are used in the instantiation stage, and it changed the instantiation procedure. Reference types proposal introduced new value types, funcref and extendref for references, new instructions for manipulating the reference values. It modified the type checking procedure, and it modified the type system, and it required a large refactoring for the type soundness proof. So a bit about the changes to the type system. So in WebAssembly, instruction sequences are typed by stack type, which consists of a tuple of lists of operand types, which represent what kind of values are being consumed and produced on the stack. The operand type can be either a value type or a bottom. So this bottom type has been introduced in Wasm 2.0. One of the motivations for introducing that was to simplify the type checking procedure of unreachable code, and this bottom type can only arise in typing unreachable code. And there is a subtyping relationship for operand types, so that relationship is reflexive, and the bottom is a subtype for any other type. Wasm 2.0 spec contained some bugs in defining typing rules for instruction sequences. Those bugs were spotted previously in WasmCert-Coq, and we implemented a corresponding fix, which is also a similar fix as in Wasm 3.0. So one part of that fix was introducing subtyping rule for stack types. And also, here are the rules for typing of instruction sequences. So the subsumption rule, it is a rule that uses that subtyping rule of stack types, and it replaces previously used weakening type rule. Now, a bit about the metrics of the code change in the mechanization. So overall, the mechanization grew from 20,000 lines of Isabelle code to 27,000 lines of Isabelle code, which is an increase of roughly a third. Significant changes were needed for type soundness, type checker, interpreter, and instantiation. One thing to note is that the type checker actually, the type checking procedure got simpler, and like the number of lines for the type checker definition and the soundness proof actually shrank, even though the language expanded. Now I'm going to talk about optimizing the verified interpreter, which is, well, one part of the mechanisations. So in the mechanized language semantics, Wasm memory is represented as a linked list of bytes. And to specify stateful operations that mutate the memory, there are two functions used, memrep write bytes and memrep read bytes, which are defined in standard functional list functions such as take, drop, and append. So an interpreter does not necessarily have to use the same representation and the same functions to model WebAssembly memory. But if you want to verify it, perhaps the easiest way is to remain close to the semantics and use the same representation. So for instance, if we use the same representation of memory, the flow for i32 store instruction could be simplified in this way. Well, we pop a constant and an address from the stack, we serialize the address, and we write the serialized bytes to the address using memrep write bytes. And in the extracted OCaml code, the memories are expected to the list. The issue is that, well, this is inefficient because these memory access operations on the functional list, they have linear complexity in the address. So then the question is, can we make the verified interpreter more efficient? Because, well, we would expect memory mutation procedures have roughly constant complexity. And one way we could do this is to use a different OCaml data structure for memory representation. So one of the structures is OCaml bytes, which is a mutable data structure for sequences of bytes. But since it is mutable, for the extraction to be sound, we have to model the mutability, like the verified interpreter has to model that mutability. This has been previously done in WasmCert-Isabelle project, which took Wasm 1.0 together with SIMD extensions and made a verified monadic interpreter that had this state monad for the memories. But this made the interpreter more complicated, more difficult to maintain, and, well, it requires additional verification effort. So then the question is, maybe there is a data structure that has, similar interface or similar semantics as immutable functional lists, but it has maybe better performance for our use case. And, well, yes, there is one such data structure. It's persistent arrays, which is, well, a persistent data structure that has been previously used in WasmCert-Coq mechanization to optimize stateful operations. And now I'm going to explain a bit what is a persistent array. So p-array basically wraps a single mutable array, and it can have multiple nodes which represent different versions of that array. So each node could either point to that single version of a mutable array, or it could point to a different node together with the information of the difference between the two nodes. So on the left we have some pseudocode for manipulating p-arrays. So we initialize a node x, which points initially to the list of array of size 5 of characters A, and then we can define y to be a modification on x, and then, well, x does not point at the array itself, it points towards y. So this means that x is the same as y, with zeroth position being replaced by character A. We can further define z in terms of w, and we have a different graph. And moreover, we can define w, which is not defined in terms of the most recent version of the array z, but it can be defined in terms of an older version, and then the graph is being rerouted. So now we have 4 nodes, and we have this graph of differences between the nodes, and all of these nodes, in principle, all of these nodes can be reconstructed if they are needed. And this data structure is perhaps the most efficient when you are most of the time accessing recent versions of the array. And yeah, we can use p-array and extract memrep write bytes and memrep read bytes to use p-array set and get functions. But the issue is that the default interface of p-array only allows manipulating a single element of the array, so it only allows byte by byte memory manipulation. So a simplified flow of I32 store could be, well, we pop a constant C and an address, serialize it into the bytes, and then we iterate through the byte list, setting each byte one by one into the memory. Yeah, but most of the operations in most of the memory operations in WebAssembly operate multiple bytes, so p-array could be inefficient. To address this, we implemented a persistent data structure on top of OCaml bytes. So this data structure has an interface for manipulating multiple bytes at once, or multiple integers of different widths. So then, if we have a function memrep write I32, which uses p bytes set in 32, then the flow of a store instruction could be, well, we pop a constant and address from the stack, and we write it into the memory using p bytes interface. Well, and this requires fewer machine instructions. Now, there are some further ways that we can could potentially optimize the interpreter. And one of the bottlenecks that we spotted was the bulk memory operations. So in the semantics, the bulk memory operations could potentially push multiple values and instructions to the stack. And we have, well, to illustrate this, we have this memory fill, the semantics for memory fill operation. There are three cases. So the first and second case are maybe less interesting. In the first case, well, this is the trap case in case we try to fill memory outside the bounds. In the second case, well, the instruction sequence terminates because, well, we are trying to write only 0 bytes. The third case is the most common case. If we try to write n plus 1 bytes, so I mean more than 1 bytes, there are instructions issued to write a single byte, and then there's another instruction sequence issued to write the remaining bytes into memory. And the interpreter, since it follows those semantics closely, it kind of also performs these kinds of pushing of multiple instructions to the stack. Well, it could be obviously optimized to implement the bulk memory operations actually in bulk without pushing the instructions to the stack. But, well, the issue is that it would require significant refactoring of the interpreter soundness proof. As right now, it heavily relies on one key lemma, and it is one of the most difficult lemmas to prove. And that lemma, well, says that a single step in the interpreter corresponds to a single reduction in the language semantics. Now, we also have some benchmarks for running the WebAssembly reference interpreter and WasmCert-Isabelle interpreter with different interpretations of different representations of memory. So if we run this on Wasm 2.0 test suite, the reference interpreter is the fastest. WasmCert-Isabelle with p bytes, well, is 20% slower, and well, WasmCert-Isabelle with list takes a reasonably long amount of time. Well, if we exclude some tests that utilize heavily the bulk memory operations, we actually can get WasmCert-Isabelle to be faster than the reference interpreter. Yeah, and for conclusion, well, WasmCert-Isabelle now fully covers Wasm 2.0. So far, WasmCert-Isabelle has been a handwritten mechanization, and you saw how much effort it takes to update it, even though like Wasm 2.0 is a smaller extension compared to what is going to be Wasm 3.0. So we hope that the update to Wasm 3.0 and further maintenance effort would be aided by SpecTech. We investigated ways to make the verified interpreter faster or try to check what are the main bottlenecks. And well, to speed up the interpreter, we implemented p-bytes data structure, which is a persistent data structure built on top of OCaml bytes. And WasmCert-Isabelle with this achieved a comparable performance with the reference interpreter, or beating the reference interpreter if we exclude bulk memory operations. Yeah, that's all.
Great, thanks so much. Questions for the speaker?
Thank you for your talk. So can you quantify, like in terms of person years, how much is the effort for you to upgrade from Wasm 1 to Wasm 2? Well, you showed the number of lines, but...
Okay, so it's probably a few months. It's like 3 or 4 months, maybe. Yeah, I would say 3 months. That's that was the effort for me to update. Yeah, to incorporate bulk memory operations and the reference types proposals.
Okay, and my second question was that, like, it feels that your PRI or p-bytes is a bespoke optimization for like a certain sort of operations that you need to do in Wasm 2. So I was wondering, like, how much in that perspective, like, SpecTech can help, because well, SpecTech doesn't really generate an optimizing interpreter.
So SpecTech, there are many parts of the mechanization. Interpreter is maybe just one of them. SpecTech could definitely generate definitions. Perhaps something bespoke would have to be built on top of SpecTech to optimize the interpreter. Like if we wanted SpecTech to emit a fast verified interpreter.
Cool. Thank you.
Okay, I have a question. Which instruction did you spend the most time on in the type soundness proof?
So it's probably some of the bulk memory instructions. So memory fill, it's comparatively simple. Maybe memory copy, it took a long time, because there are maybe 4 cases and they're pretty long. Yeah.
Yeah, for reference, this is because we decided we wanted to specify that depending on whether the destination or the source address is bigger, you copy in an opposite direction to make it unobservable, which means you have twice as many cases to handle. Okay, let's thank the speaker one last time.